Right now, a spacecraft built in the 1970s is traveling through interstellar space at 17 kilometers per second. It has been flying, without slowing, without stopping, for nearly 50 years. And every single day, engineers at a research facility in California sit down at their computers, type out commands, and send them across 24 billion kilometers of empty space to a machine running on 68 kilobytes of memory. That signal, traveling at the speed of light, takes 23.5 hours to arrive. The reply takes another 23.5 hours to return. And yet, the connection holds. This is not a metaphor. This is not a dramatic framing device. This is literally happening right now. Voyager 1 is the most distant human-made object in existence, and the team responsible for keeping it alive consists of just 10 people. To understand how that is even possible, you have to go back to a discovery made not by a scientist, but by a graduate student. In 1964, a young researcher at NASA's Jet Propulsion Laboratory named Gary Flandreau was working on trajectory calculations when he noticed something unusual in the orbital mathematics of the outer solar system. Once every 176 years, the four giant planets, Jupiter, Saturn, Uranus, and Neptune, align in a sweeping arc that creates an extraordinary opportunity. A spacecraft launched at precisely the right moment, on precisely the right path, could use the gravity of each planet to slingshot toward the next one, gaining speed with every pass, covering in 12 years what would otherwise require 30. It was a window that would not open again until the 2100s. NASA called the proposed mission the Grand Tour. They planned 4 spacecraft. Then the Apollo era ended, budgets contracted, and the program was cut down to 2 probes. 2 chances. That was the compromise. And in the summer of 1977, both of them launched from Cape Canaveral within weeks of each other. Voyager 2 went first, in late August, on a longer curved path that would carry it past all 4 outer planets. Voyager 1 followed in early September, on a faster, more direct trajectory aimed at Jupiter and Saturn. The names are confusing. Voyager 2 left first. Voyager 1 arrived at its targets first. But the logic made sense at the time, and both probes had their own specific jobs to do. Each one carried a gold-plated copper disc, a kind of time capsule intended for whoever or whatever might someday find it. The disc contained greetings in 55 languages, 115 images of Earth, and 90 minutes of music from cultures across the planet. The idea was simple and audacious. If either probe were ever recovered by another intelligence, this disc would tell them something true about the civilization that built it. But setting aside the philosophical implications, the primary purpose of both spacecraft was scientific. Photographs of worlds no human eye had ever seen up close, magnetic field measurements, atmospheric readings, particle detectors, a suite of 11 scientific instruments packed into a spacecraft about the size of a small car. What they found exceeded almost every expectation. When Voyager 1 reached Jupiter in March of 1979, it sent back images that completely reframed what scientists understood about the outer solar system. Jupiter's atmosphere was not the simple banded gas cloud they had expected. It was a churning, violent system of storms, with winds exceeding 500 kilometers per hour and a great red spot large enough to swallow 2 Earths. But the real surprise came from one of Jupiter's moons. Io, the innermost of the 4 large Galilean moons, turned out to be the most volcanically active body in the entire solar system. Voyager 1 captured active eruptions in progress, plumes of sulfur dioxide shooting hundreds of kilometers above the surface. Nobody had predicted this. The volcanism is driven by tidal heating gravitational stress from Jupiter and the other large moons constantly squeezing and stretching Io's interior, generating enough heat to keep the surface perpetually molten. It was a completely new mechanism for planetary geology, discovered by a spacecraft on a flyby. Voyager 2 made the same journey and confirmed the findings. Then both probes continued towards Saturn, arriving in 1980 and 1981 respectively. Saturn's rings turned out to be far more complex than anyone had guessed. Instead of a few broad bands, the ring system was made up of thousands of individual ringlets, sculpted by gravitational resonances and small embedded moons. The rings had waves in them, spiral patterns, gaps that appeared and disappeared, a dynamic system that was still evolving. Saturn's moon, Titan, revealed a thick orange atmosphere, suggesting the presence of complex organic chemistry at temperatures of around -179 degrees Celsius. Scientists immediately began wondering whether anything could survive there. After Saturn, the two probes went their separate ways, literally. Voyager 1, having completed its primary mission, was swung north by Saturn's gravity onto a trajectory that would carry it directly out of the solar system. At 17 kilometers per second, it would never slow down, never return. No further planetary encounters, just an endless coast into the dark. Voyager 2, on a different path, continued south and outward, making the first and only visits to Uranus and Neptune in 1986 and 1989. At Uranus, it discovered that the planet was tilted on its side, rotating with its poles nearly in the plane of its orbit, and revealed a system of narrow rings with bizarre kinked structures. At Neptune, it found an active atmosphere with the fastest winds measured anywhere in the solar system, winds exceeding 2,100 kilometers per hour, and a large dark storm, comparable in some ways to Jupiter's great red spot. It also flew close to Neptune's large moon Triton, which turned out to have active nitrogen geysers erupting from a surface coated in frozen nitrogen and methane. These were the only close-up observations humanity would get of Uranus and Neptune for decades. As of right now, no other spacecraft has visited either planet since. After Neptune, Voyager 2 followed its own trajectory out of the solar system, heading south and into interstellar space. The two probes were now moving in opposite directions, carrying identical golden records on separate paths through the cosmos. Before heading fully dark, Voyager 1 performed one final observation. In February of 1990, at the request of astronomer Carl Sagan, it turned its camera back toward the inner solar system and took a photograph. Earth appeared as a single pale blue pixel, a tiny dot suspended in a scattered ray of sunlight, diffracted through the camera optics. Sagan later described the image in terms that said something profound about scale, perspective, and the nature of human civilization. The image became known as the pale blue dot, and it remains one of the most widely reproduced photographs in the history of space exploration. Then the cameras were turned off to save power, and Voyager 1 continued its journey into the void. The question of how we stay in contact with it begins with the hardware the spacecraft carries. Each Voyager is equipped with a parabolic dish antenna, 3.7 meters in diameter. For a spacecraft, that is a substantial antenna. The dish is designed to focus all outgoing transmissions into a narrow beam aimed precisely at Earth, and to collect incoming signals and concentrate them at the receiver. The transmitter that drives this dish operates on roughly 23 watts of power, about the same as a dim household light bulb. That is the total broadcast power of a spacecraft screaming across 24 billion kilometers of vacuum. 23 watts. The transmitter operates at a frequency of 8.4 gigahertz in the X-band of the radio spectrum. This frequency was chosen because it passes cleanly through the Earth's atmosphere, with minimal absorption, and because at that wavelength, a parabolic dish of reasonable size can focus the beam tightly enough to still be detectable at interstellar distances. Even so, by the time the signal completes its journey across the solar system, it arrives at Earth carrying less than 1 attowatt of power. 1 attowatt is 10 to the power of negative 18 watts, 1 billionth of a single watt. It is a number so small, it exists below the threshold of almost any practical measurement. To put it in some kind of context, a digital watch battery outputs roughly 1 milliwatt of power when driving the display. Voyager's arriving signal is approximately 20 billion times weaker than that. This is not a signal. It is a whisper in the noise floor of the universe. Receiving it requires something extraordinary on the ground. NASA built 3 receiver complexes specifically for this purpose, placed at roughly equal intervals around the Earth at 120 degrees of longitude apart. There is one in the Mojave Desert of California, near a town called Goldstone. There is one outside Madrid, in Spain, and there is one outside Canberra, in Australia. Together, these 3 stations constitute the Deep Space Network, one of the most sensitive radio receiving systems ever constructed. The spacing is deliberate. As the Earth rotates, each station moves in and out of view of different parts of the sky. By positioning the 3 complexes roughly evenly around the planet, there is always at least one station with line of sight to any spacecraft anywhere in the solar system. When one station rotates out of contact, another rotates into position. The signal chain is continuous. The primary receiving antennas at each complex are 70 meters in diameter dishes, so large they can be seen from several kilometers away. These are among the largest fully steerable radio telescopes on Earth. The collecting area of a 70-meter dish is roughly 3,800 square meters. Every square meter gathers a tiny share of the incoming signal, and the parabolic shape focuses all of it onto a single receiving element at the focal point. But collecting area alone is not sufficient. At the power levels involved with receiving Voyager, the thermal noise generated by room temperature electronics is overwhelming. The thermal agitation of electrons in any conductor at normal temperatures produces a background of random electrical noise that would completely bury Voyager's signal. To overcome this, the receiving equipment is cryogenically cooled to approximately 4 degrees Kelvin, 4 degrees above absolute zero, using liquid helium refrigeration systems. At these temperatures, the thermal noise drops to a level where the incoming signal can be detected. Even after cooling, separating Voyager's actual data from the surrounding noise requires sophisticated signal processing. The data rate from Voyager 1 is now just 40 bits per second for comparison. A modern broadband connection can carry hundreds of millions of bits per second. 40 bits per second is a data rate so low it could barely transmit a short text message in a full minute. This is the bandwidth humanity has to the edge of the solar system. And even that rate was only achieved after NASA updated the signal processing algorithms on the ground to extract more information from the same amount of received power. There is one more complication. Voyager 1 is moving away from Earth at 17 kilometers per second. This means every radio wave it transmits is slightly stretched by the Doppler effect before it arrives at the receiver. The same phenomenon that makes a passing ambulance's sirens seem to drop in pitch, in the waves are compressed by motion towards you and stretched by motion away from you, applies to Voyager's radio signal. The frequency shift is small but measurable, and if the ground stations did not compensate for it, the signal would drift out of the tuning window of the receiver. The team must continuously calculate Voyager's velocity and adjust the receiver's frequency in real time to stay locked on the signal. And then there is the delay, 23.5 hours each way. When an engineer at the Jet Propulsion Laboratory sends a command to Voyager 1 on a Monday morning, the command will not arrive until Tuesday morning. The response will not return until Wednesday morning. 2 days to complete a single exchange. This is not a frustrating technical limitation. It is simply the physics of a universe where nothing, not even information, travels faster than the speed of light. Managing a spacecraft across those timescales requires extraordinary discipline. Every command must be carefully verified before transmission because there is no possibility of a quick correction. A mistake takes 2 days to discover. Yet the team has been doing exactly this, successfully, for nearly 50 years. The spacecraft themselves are not passive during those waiting periods. Each Voyager carries 3 onboard computers, an attitude control system, a flight data system, and a command control system that manage routine operations autonomously. They maintain the antenna's pointing direction, monitor temperatures and power levels, and execute pre-programmed command sequences without waiting for instruction. The computers have 68 kilobytes of memory between them. A modern smartphone carries several hundred gigabytes of storage, roughly 4 million times more. And yet these tiny machines have been running continuously without error recovery from physical hardware failure in the thermal and radiation environment of deep space for nearly 50 years. The power source is equally unusual. Each Voyager does not carry solar panels. At the distance of Jupiter, sunlight is 25 times fainter than it is at Earth. And at the distance Voyager has now reached, it is essentially negligible. Instead, each spacecraft carries 3 radioisotope thermoelectric generators of compact devices that convert heat from the natural radioactive decay of plutonium-238 directly into electricity. The thermoelectric conversion works through the Seebeck effect. When one end of a semiconductor is kept at a different temperature than the other, a voltage develops. No moving parts, no combustion, just nuclear decay, heat, and a temperature gradient. When the Voyagers launched, each set of 3 radioisotope thermoelectric generators produced 470 watts. The plutonium has been decaying for nearly 50 years now, and the power output has dropped to approximately 210 watts per spacecraft. Each year, the output falls by roughly 4 watts. 210 watts is not a lot. A standard desktop computer consumes more than that, and every instrument on board, every sensor, every heater keeping the electronics from freezing, every transmitter draws from that same pool. As power has declined, the team has been forced to shut down instruments one by one, selecting which scientific observations to sacrifice in order to keep the spacecraft functioning. Of the 11 original instruments on each Voyager, only 3 remain operational on Voyager 1 as of the mid-2020s. One of those 3 is the magnetometer, a long, boom-mounted instrument that measures the direction and strength of the surrounding magnetic field. It was this instrument that provided the definitive evidence of something scientists had been waiting decades to confirm. The sun continuously emits a stream of charged particles called the solar wind. This outflow of plasma expands outward in all directions, forming a vast bubble of solar influence called the heliosphere. The boundary of the heliosphere, where the solar wind finally loses enough energy to be overwhelmed by the interstellar medium, the thin gas and magnetic field that fills the space between stars, is called the heliopause. No spacecraft had ever crossed this boundary before. Nobody knew exactly where it was, or what crossing it would feel like to an instrument. On August 25th, 2012, Voyager 1's magnetometer registered an abrupt and sustained shift in the magnetic field environment surrounding the spacecraft. The direction of the field changed. The character of the particle population changed. The turbulent, compressed region just inside the heliopause gave way to a calmer, organized magnetic field aligned with the broader galactic structure. The plasma density measurements confirmed it. Voyager 1 had left the heliosphere. It was now in interstellar space. This was the first time any object built by humans had crossed that boundary. After 35 years of travel, Voyager 1 had reached the space between the stars. Not the nearest star that is still thousands of years away at its current speed, but the vast ocean of gas and dust and ancient magnetic fields that fills the galaxy between stellar systems. Voyager 2 crossed the heliopause in November 2018, confirming that the boundary is not perfectly spherical. Voyager 2, traveling in a different direction, crossed at a slightly different distance from the Sun, providing scientists with two independent measurements of the heliosphere's extent. Keeping the connection alive across those distances has not been straightforward. The history of both spacecraft is marked by crises that should have ended the mission, and by engineers who refused to let them. The first major near loss happened in 1978, just 8 months after launch. Voyager 2 carries two radio receivers, a primary and a backup, because reliability across a 50-year mission was always going to require redundancy. A scheduling error on the ground resulted in Voyager 2 going without contact for 7 days. When a spacecraft designed to expect daily communication goes dark for a week, its onboard fault protection software interprets this as a hardware failure. The software assumed the primary receiver had failed and automatically switched to the backup. The backup had a broken capacitor. It could receive signals, but only at a very specific and slightly offset frequency, one that the engineers on the ground did not know. When they tried to command Voyager 2 back to its primary receiver, the command did not register on the damaged backup. The fuses for the primary receiver blew. Voyager 2 was now locked on a broken backup receiver, 8 months into a mission designed to last decades. The engineers at the Deep Space Network Station in Madrid began methodically sweeping through a range of frequencies around the expected value, transmitting test signals at each frequency, and waiting to see if Voyager 2 acknowledged them. They were searching, in effect, for the exact offset caused by the broken capacitor. After hours of systematic searching, a response came through. Voyager 2 had heard them. The engineers had found the broken receiver's listening window, and they have been exploiting that same workaround ever since. For nearly 50 years, every command sent to Voyager 2 has been transmitted at the precise frequency required by a capacitor that broke in 1978. In January 2020, a routine calibration maneuver went wrong. Two power-hungry systems on Voyager 2 were inadvertently left running at the same time, drawing more current than the spacecraft could supply. The automatic fault protection software responded instantly, shutting down all 5 of the remaining science instruments to protect the spacecraft from a catastrophic power failure. The instruments went dark. By this point, Voyager 2 was far enough from Earth that a one-way signal took 17 hours to arrive. Restoring the instruments required a series of carefully coordinated commands sent over multiple days. It took a week. Then, in 2022, Voyager 1 started sending back corrupted data. The telemetry, the stream of engineering and science data that the spacecraft continuously transmits, was suddenly unintelligible. The engineers could receive it, but what arrived looked like random noise. It took months of patient analysis to trace the problem. The flight data system, one of the 3 main computers, was storing its data correctly, but it was routing the data through a chip that had stopped working years ago before sending it to the transmitter. The dead chip was scrambling everything it touched. Once the team identified the faulty pathway, they reprogrammed the data routing to bypass the broken chip entirely. The telemetry cleared. The most dramatic incident came in 2023. Voyager 2, which had exited the heliosphere heading south, was moving in a direction that kept it out of sight of all but one Deep Space Network station, the complex outside Canberra, Australia. In July of that year, a routine command was accidentally transmitted with a 2-degree angular error that shifted Voyager 2's antenna slightly off its pointing direction. 2 degrees is nothing in everyday terms. At a distance of 20 billion kilometers, it was enough to point the dish away from Earth. The signal went silent. For 2 weeks, the team had no contact with Voyager 2. They were sending commands into space, with no confirmation they were being received. The spacecraft had no way to know it was misaligned. Its fault protection software interpreted the situation as a communication outage, and did nothing. Its automated turn toward Earth procedure was not scheduled to trigger for several months. The team waited, and listened. Then, on the 18th of August, a faint signal emerged from the noise. Voyager 2 was still transmitting. The spacecraft was still alive, still flying, still sending its automated heartbeat across the solar system. The antenna was just slightly off. The team had one chance. They commanded the Deep Space Network station in Canberra to transmit at 250% of its normal power, the absolute maximum the antenna could physically produce. The command was sent, and then they waited. 20 hours for the signal to travel out. 20 hours for the response to return. 40 hours of uncertainty. The antenna moved. Voyager 2 turned toward Earth. The signal locked. The connection was restored. Every single one of these crises, the broken receiver in 1978, the power failure in 2020, the corrupted data in 2022, the antenna misalignment in 2023, was resolved by a team of 10 engineers working with hardware they cannot touch, cannot replace, and cannot inspect, across distances that make every decision a 2-day commitment. The physics behind the communication link itself is worth sitting with for a moment, because it represents one of the most extreme examples of signal engineering ever attempted. When engineers design a communication system, they work with something called the link budget, essentially an accounting of all the power gained and lost along the transmission path. You start with the transmitter power. Add the gain from the transmitting antenna's ability to focus the beam. Subtract the spreading of the signal across the distance between transmitter and receiver. Add the gain from the receiving antenna's collecting area, and account for noise at the receiver. What you end up with is the received signal-to-noise ratio, which determines whether the signal can be decoded at all. For Voyager 1 at its current distance, the numbers are extreme. The transmitter puts out 23 watts. The Voyager dish antenna focuses this into a beam about 1/10 of a degree wide, providing substantial gain over an omnidirectional transmitter. But the signal then has to travel 24 billion kilometers, and as it spreads outward, its power drops as the square of the distance. By the time it reaches Earth, the signal has been diluted across a sphere with a radius of 24 billion kilometers. The total power spread across that sphere is minuscule. The 70-meter dish at Goldstone intercepts a tiny fraction of that sphere, an area of roughly 3,800 square meters, out of an expanding shell with a total surface area of approximately 7.2 times 10 to the 24th power square meters. And yet, it works. The combination of the cryogenically cooled receiver, the massive collecting area, and sophisticated signal processing algorithms manages to extract meaningful data from the noise. There is something almost counterintuitive about the fact that the ground sends a stronger signal than the spacecraft does. The 70-meter dishes at the Deep Space Network can transmit at up to 22 kilowatts, roughly 1,000 times more power than Voyager's 23-watt transmitter. This asymmetry makes sense when you think about it. The ground stations are connected to the electrical grid, have virtually unlimited power available, and carry no weight constraints. Voyager runs on 210 watts from a decaying nuclear battery. The uplink is shouting. The downlink is whispering. The data encoding also plays a crucial role. The information transmitted by Voyager is encoded using error-correcting codes, mathematical techniques that add carefully structured redundancy to the data stream, allowing the receiver to reconstruct corrupted or missing bits. Reed-Solomon coding and convolutional coding are layered together, and over the years, engineers on the ground have updated the decoding algorithms to extract more information from the same received power. The science data rate from Voyager 1 in the early years of the mission was 160 bits per second. Today it is 40 bits per second, and every one of those bits carries hard-won information from beyond the edge of our solar system. The pointing of Voyager's antenna deserves attention as well. The 3.7-meter dish must remain pointed at Earth within a fraction of a degree to maintain the communication link. At the distances involved, a pointing error of even 1 degree would move the beam completely off Earth. The attitude control system uses 3-axis gyroscopes and a star tracker to determine orientation, and small hydrazine thrusters to make corrections. The gyroscopes on Voyager 1 have been running for nearly 50 years. The hydrazine propellant, which was loaded before launch, is almost depleted, but enough remains to maintain pointing for the foreseeable future. Interestingly, one of the reference stars that Voyager 1 uses for navigation is Canopus, a bright star in the southern sky. When Voyager needs to confirm its orientation, it looks for Canopus in a specific position relative to the Sun and uses this triangulation to verify its pointing. A spacecraft built in the 1970s is navigating by starlight, just as sailors did centuries before it. The science being returned from these instruments, sparse as the data stream has become, continues to be genuinely new. Voyager 1 is measuring the density of the interstellar medium, the strength and direction of the interstellar magnetic field, and the flux of cosmic rays arriving from outside the solar system. Before Voyager, these measurements were essentially unavailable theoretical models existed, but no direct observations had been made in situ. The data being collected now forms the foundation of interstellar space physics as a discipline. One of the key findings from the heliopause crossing was that the boundary between the heliosphere and the interstellar medium is sharper than many models had predicted. Some theoretical frameworks had suggested a gradual transition region extending tens of billions of kilometers. What Voyager measured was a relatively abrupt boundary, a relatively narrow zone where the character of the plasma environment shifted decisively. The interstellar magnetic field outside the heliopause is organized along a different direction than the solar wind's field inside, reflecting the structure of the broader galactic magnetic field in the local neighborhood of the Sun. This has implications for understanding how the solar system interacts with its galactic environment. The heliosphere acts as a kind of shield, deflecting some fraction of the cosmic rays, high-energy particles, accelerated by distant supernova explosions, and other violent events that would otherwise reach Earth. Understanding the shape and boundary of this shield is directly relevant to questions about radiation environments for future deep space missions, and about how much cosmic radiation complex life on Earth has actually been exposed to over geological time. Voyager 2's crossing in 2018 allowed scientists to compare conditions at 2 different points on the heliopause boundary, separated by about 150 astronomical units in distance. 1 astronomical unit being the average distance from Earth to the Sun. The comparison revealed that while the general characteristics of the crossing were similar, the specific conditions differed in ways that suggest the heliopause is not a simple uniform boundary. It has structure, variations in thickness and intensity, shaped by the interaction between solar wind and the local interstellar medium, in ways that are not yet fully understood. The 2 probes also detected a previously unknown layer just inside the heliopause, where the solar wind slows dramatically and becomes compressed and heated before crossing the boundary. This region, called the heliosheath, is where the solar wind is essentially breaking against the resistance of the interstellar medium. The process produces energetic neutral atoms that have since been detected by other spacecraft and used to map the shape of the heliosphere from the inside, complementing the in-situ measurements from the Voyagers. What is perhaps most remarkable is that the instruments measuring all of this were designed in the 1960s and early 1970s, built and calibrated in the mid-1970s, and have been operating continuously ever since. The magnetometer boom on Voyager 1 extends 13 meters from the spacecraft body and carries sensors that were calibrated on Earth before the spacecraft left. They have been exposed to the thermal cycling of deep space, the radiation environment of the outer solar system, and nearly 50 years of continuous operation. And they are still returning data that is scientifically useful, data that cannot be obtained any other way. The question of what comes next for the Voyager mission is straightforward in outline but poignant in specifics. The power output of the radioisotope thermoelectric generators continues to decline at roughly 4 watts per year. As power drops, the team must periodically shut down heaters that protect certain components from the cold of space. When a component's temperature drops below its operating limit, it may fail. Some failures will be recoverable, others will not. The science instruments are being shut down one by one to preserve power for the communications systems in the computers. The team's goal is to keep at least some instruments running through the 50th anniversary of the launches in 2027. They hope to extend operations to perhaps 2028 or 2030, depending on how the power curve develops and whether any new failures occur. At some point, the team is realistic about this. The last instrument will go silent. Then, the transmitter itself will lose power, or a hardware failure will sever the link and the signal will stop. When that happens, the spacecraft will not stop. They will continue on their current trajectories, traveling at 17 kilometers per second through interstellar space for millions of years. They will not encounter another star for approximately 40,000 years in Voyager 1's case, when it will pass within approximately 1.6 light years of a small red dwarf star called AC plus 79,388. In roughly 300,000 years, Voyager 2 will pass within about 4 light years of Sirius, the brightest star in Earth's sky as seen from our solar system. Neither spacecraft will enter another stellar system. The distances are too vast, and the trajectories are not aimed precisely enough, but they will drift through the galaxy as silent emissaries for longer than modern humans have existed as a species. The golden records they carry were designed on that timescale. Gold is essentially chemically inert in vacuum. The disks are protected by aluminum covers. The information is encoded as physical grooves that can be read mechanically without any prior knowledge of human technology. The cover provides a diagram explaining how to play the record and what the contents represent, expressed in mathematics and pulsar timing data that serve as a kind of universal key. Whether any intelligence will ever find and decode them is unknowable. The probability is vanishingly small on any reasonable timescale. But the records were included, not because of any realistic expectation of contact, but as a statement about the civilization that launched them, a civilization that was capable of thinking, at least briefly, on a galactic scale. Scientists have been thinking seriously about what a next-generation interstellar probe might look like, and the contrast with the Voyagers is striking. The computing technology alone has changed by a factor of millions. A modern spacecraft processor operates at billions of cycles per second and can execute vastly more complex algorithms with correspondingly less power. Artificial intelligence and autonomous navigation systems could allow a next-generation probe to diagnose its own faults, reconfigure its instruments, and adjust its course without waiting for commands from Earth. The kind of crises that required weeks of painstaking troubleshooting from the Voyager team might be resolved automatically in seconds. Communications technology has advanced as well. Laser communication using tightly focused infrared beams instead of radio waves can carry vastly more data across the same power budget, because the beam is much narrower and loses less energy to spreading. NASA has been testing laser communication systems on missions in the inner solar system, and the technology is advancing rapidly. A Voyager-equivalent spacecraft equipped with a laser communication system could return data at rates hundreds of times higher than the current radio link, despite operating at the same or less power. Propulsion is the harder problem. Chemical rockets cannot get a spacecraft to interstellar space on any useful timescale. Voyager used gravitational assists to reach its current speed. A modern mission using the same technique would achieve comparable speeds. To go significantly faster requires either a more powerful gravitational assist using the sun itself, a technique called an Oberth maneuver, where a rocket fires at the point of closest approach to the sun to take maximum advantage of the sun's gravity well, or an entirely different propulsion technology. Solar sail concepts, which use the pressure of sunlight to accelerate a lightweight spacecraft, have been tested at small scales. In theory, a sufficiently large and lightweight sail could accelerate a small probe to several times Voyager's speed, potentially allowing it to overtake both Voyagers within a few decades. A nuclear pulse propulsion concept could achieve even higher speeds, though the engineering and regulatory challenges are substantial. There is also a periodicity to consider. The grand planetary alignment that enabled the Voyager Grand Tour, the configuration that allows a single spacecraft to visit all 4 giant planets, returns in the 2050s. Not quite the same alignment, but close enough to allow a new multi-planet mission to reach the outer solar system in significantly less time than a direct trajectory. Planetary scientists have been advocating for an ice giant mission to Uranus or Neptune for decades, and a favorable launch window exists in the late 2030s that would allow a spacecraft to reach Uranus in roughly 10 years. Whether that mission will be funded and launched in time is a question that depends on policy and resources as much as on science. In the meantime, the Voyagers fly on. Each day, the signal that left Voyager 1 almost a full day ago arrives at the 70-meter dish in California or Spain or Australia. Each day, the 10 engineers at the Jet Propulsion Laboratory decode that signal, assess the state of the spacecraft, and decide what commands to send back. Each day, Voyager 1 moves another 1.5 billion kilometers further from home, reaching a region of space no human-built instrument has ever sampled before. The science being returned is genuinely irreplaceable. No model of the heliosphere or the interstellar medium can fully substitute for direct measurement. The data Voyager 1 and Voyager 2 are sending back right now represents the only in situ observations of the very local interstellar medium that science has or will have for the foreseeable future. Everything beyond the heliopause, the density and temperature of the interstellar gas, the strength and orientation of the interstellar magnetic field, the spectrum and flux of cosmic rays in their pristine form before they are modified by the solar wind, is being measured for the first time. There are still significant open questions in interstellar physics that the Voyagers are helping to address. The shape of the heliosphere is not well known. Some theoretical models predict a roughly spherical bubble. Others predict a comet-like shape, elongated in the direction of the sun's motion through the galaxy and compressed on the leading edge by ram pressure from the interstellar medium. The two Voyager crossing points give scientists reference measurements along two different directions, but this is far from sufficient to map the full three-dimensional shape of the boundary. Determining the heliosphere's shape requires either more probes crossing the boundary in other directions or indirect remote sensing techniques using energetic neutral atom maps. The interstellar magnetic field direction and strength near the solar system turn out to matter for questions about cosmic ray transport, about how energetic particles from supernova explosions propagate through the galaxy, and about the long-term radiation history of the inner solar system. Voyager's measurements of this field are the first direct data points ever obtained, and they have already challenged some theoretical assumptions. More measurements from different directions would help substantially. There is also the broader question of what the local interstellar medium is actually like. The sun is currently moving through a region of relatively warm, low-density gas called the local bubble, the remnant of a series of supernova explosions that occurred millions of years ago. The properties of this environment, its temperature, its ionization state, its magnetic field structure, are not uniform, and the sun has been moving through it for millions of years. Understanding this environment has implications for paleoclimatology, because changes in the cosmic ray flux reaching the inner solar system over geological time may have influenced Earth's climate on very long timescales. All of these threads connect back to data that two spacecraft launched in 1977 are still collecting and transmitting today. The engineering achievement embedded in this is easy to understate. These spacecraft were designed for 5-year primary missions. The electronics were built using transistor technology from the early 1970s. The software was written in assembly language on machines that filled rooms, and then loaded onto the spacecraft before launch. No subsequent modifications to the hardware have been possible. Every change since launch has been a software update transmitted across billions of kilometers and executed by a computer with 68 kilobytes of memory. And yet here we are, 48 years later, still in contact, still receiving science data, still sending commands and having them executed. The Voyager mission is sometimes described as humanity's greatest engineering achievement, and while that claim is subjective, it is not difficult to see why people make it. No other human-built object has traveled as far. No other mission has remained operational for as long on its original hardware. No other probe has crossed into interstellar space. The people who built these spacecraft engineers, who were young in the 1970s and are now retired or gone, did not know they were building something that would still be working 5 decades later. They designed for the planets. They got the stars. Not literally, not yet. The nearest star is still tens of thousands of years away, but the principle holds. They aimed for Jupiter and Saturn, and what they built outlasted every reasonable expectation and became, quietly, one of the most extraordinary long-duration experiments in the history of science. The power will run out, maybe in 2028, maybe in 2030. At some point, the last instrument will fall silent, the last data packet will be received, and the signal from Voyager will fade below the noise floor of even the most sensitive receiver on Earth. The connection will be lost, but the spacecraft will still be there. 17 kilometers per second, a direction determined by the gravity of a planet it flew past in 1980. A golden record on its side that has been tumbling through interstellar space since the Carter administration. The sounds of rain and ocean waves and a child's laughter and music from dozens of cultures, stored in physical grooves on a gold disc that will outlast every structure humanity has ever built on Earth. The signal will stop. The journey won't. To fully appreciate what the Voyager mission represents, it helps to understand the engineering environment those spacecraft have been operating in for nearly 50 years. Space is not simply empty. The region beyond Earth's magnetic field is permeated by charged particles, protons, and electrons, accelerated by solar flares and coronal mass ejections, cosmic rays arriving from outside the solar system, ultraviolet radiation, with no atmospheric filter. This environment is hostile to electronics in ways that are difficult to engineer around completely. Integrated circuits, the transistors and logic gates that form the brains of every electronic device, can be disrupted or permanently damaged by energetic particles passing through their silicon substrates. A high-energy proton colliding with a transistor can flip a bit in memory, change the state of a logic gate, or deposit enough charge to cause a latch-up condition that permanently fuses a circuit. In Earth orbit, astronauts and spacecraft experience these events regularly. Deep space probes, beyond the protection of even the heliosphere's attenuated particle shielding, are exposed to even higher fluxes of cosmic rays. The Voyager computers were designed to survive this environment through redundancy, careful shielding, and programming that would detect and correct common fault types automatically. Memory registers were protected with parity bits that can flag when a value has been flipped by a particle strike. Critical sequences were stored in multiple locations and cross-checked against each other. The spacecraft were designed to fail gracefully, to fall back on backup systems, to wait patiently for new instructions, to maintain communication even if science instruments failed. This design philosophy is why the Voyagers have survived. Not every system on board has made it. Chips have failed, instruments have degraded. The backup receiver on Voyager 2 has been running since 1978 on a broken capacitor. But the core systems, the ones responsible for keeping the spacecraft alive and connected to Earth, have kept working. There is something remarkable about that achievement from a materials science perspective alone. The electronics aboard Voyager were fabricated using semiconductor processes from the early 1970s. The feature sizes on the transistors in those chips are measured in micrometers, thousands of times larger than the nanometer scale features in a modern smartphone chip. In some ways, this coarseness is an advantage. Larger transistors are less sensitive to individual particle strikes because the deposited charge from a single cosmic ray represents a smaller fraction of the total charge stored in the device. But the larger feature sizes also mean the chips are slower and consume more power per unit of computation. The engineers who designed the Voyager systems made choices that prioritize survival over performance, reliability over speed. Looking back, those choices were exactly right. The spacecraft needed to be alive in 50 years, not fast in the first 5. The thermal environment presents its own challenges. The outer solar system, where the Voyagers have spent most of their operational lives, is cold, very cold. The temperature of a surface in thermal equilibrium at Voyager's current distance from the Sun is somewhere around -200 degrees Celsius. The spacecraft's electronics and instruments must be kept significantly warmer than this to function. Heaters, powered by the onboard electrical system, maintain critical components within their operational temperature ranges. As the power budget has tightened over the decades, some heaters have been turned off to conserve electricity, and the engineers must carefully track which components are approaching their lower temperature limits. The hydrazine thrusters that maintain pointing and spin up the gyroscopes are also affected by temperature. Hydrazine freezes at roughly -2 degrees Celsius, which is quite warm compared to the spacecraft's environment. The fuel lines and thrusters must be kept above this temperature by heaters or by managing the spacecraft's orientation to use solar heating. As power has declined, maintaining these thermal requirements has become an increasingly delicate balancing act. The gyroscopes themselves are mechanical devices, spinning wheels suspended in gimbals, maintaining orientation by conservation of angular momentum. They have been spinning continuously for nearly 50 years. The bearings have been operating in vacuum, lubricated by materials that were selected before the concept of a 50-year mission was seriously contemplated. The fact that they are still functioning is a tribute both to materials engineering and to some degree of luck. Understanding how any of this was designed requires stepping back to the engineering culture of the 1960s and 70s at the Jet Propulsion Laboratory. The institution had been built during the space race, and its engineers had an approach to reliability that was shaped by the extreme consequences of failure and the impossibility of repair. A spacecraft that failed at Jupiter could not be retrieved. There was no second mission planned. Every component, every wire, every solder joint had to work correctly from the first power on in 1977 through however long the mission lasted. This approach, sometimes called reliability engineering, sometimes just called building things right, involved extensive testing at temperatures and pressures and radiation doses beyond what the spacecraft was expected to encounter, building in margins that accounted for unknown unknowns, using materials with long flight heritage, and designing systems that would degrade gracefully rather than failing catastrophically. The goal was not perfection in a single measurement, but survival across decades. The Voyager team had roughly 4 years from the initial concept to launch, working with computing tools that were primitive by modern standards. The trajectory calculations that made the Grand Tour possible were done on mainframe computers that filled rooms. The software that runs the spacecraft was written in assembly language, the lowest level of programming, closest to the actual operations of the processor, because the computers on board were so limited that higher level languages would have consumed too much memory and run too slowly. Every kilobyte of memory on the spacecraft was a resource to be managed. Every watt of power had a budget. Every gram of mass had to be justified against the launch vehicle's capability. These constraints forced a kind of engineering discipline that is unusual in more modern programs where computational resources are essentially unlimited and software can be patched after delivery. The scientific return from the mission over nearly 50 years is enormous by any measure. The Voyagers were responsible for the first detailed characterization of the Jovian magnetosphere, the vast region of space dominated by Jupiter's powerful magnetic field, which turned out to be 14 times stronger than Earth's and to extend several million kilometers into space. They discovered that Jupiter's magnetosphere contained a complex system of plasmatory donut-shaped rings of charged particles shed by the volcanically active moon Io that circulate around the planet and interact with its magnetic field in complex ways. These plasmatory were completely unexpected before the Voyager encounters. At Saturn, the Voyagers made precise measurements of the ring system that still inform ring dynamics research. They measured the masses of several moons, discovered new small moons within the ring gaps, and provided the first high-resolution images of Saturn's complex cloud structures. The discovery that Titan had a thick atmosphere made it an immediate target for future exploration, the Cassini-Huygens mission, which arrived at Saturn in 2004 and dropped a probe onto Titan's surface in 2005, was directly inspired by Voyager's findings. Voyager 2's encounter with Uranus in January 1986 was the only close reconnaissance of that planet in history. The images revealed a featureless blue-green disk with almost no cloud structure visible. Uranus turned out to be among the least dynamic of the giant planets, at least in the visible wavelengths available to Voyager's cameras. But the encounter revealed 9 rings previously unknown, 10 new small moons, and provided the first measurements of Uranus's magnetic field, which turned out to be dramatically tilted relative to the planet's rotation axis, and offset from the planet's center, a configuration very different from any other planet in the solar system. The Uranus encounter also provided the first data suggesting that Uranus and Neptune are a distinct category of planet ice giants, with compositions fundamentally different from the gas giants Jupiter and Saturn. Rather than being composed primarily of hydrogen and helium, Uranus and Neptune appear to contain significant amounts of water, ammonia, and methane in high-pressure ice phases in their interiors. This distinction has proven important for understanding the formation of planetary systems in general. Statistical data from exoplanet surveys suggests that ice giants are among the most common types of planet in the galaxy. The Neptune encounter in August 1989 was the final planetary flyby of the Voyager mission, and it may have been the most scientifically surprising. Neptune's atmosphere, despite receiving almost 900 times less sunlight than Earth's, turned out to be the most meteorologically active in the solar system at the time of the encounter. The Great Dark Spot, a storm system comparable in size to Earth, was visible on Neptune's disk. Wind speeds, measured by tracking cloud features, exceeded 2,000 kilometers per hour faster than any storm ever recorded anywhere. Neptune's moon Triton proved to be one of the strangest objects in the solar system. It orbits in the opposite direction from Neptune's rotation, a retrograde orbit that suggests Triton was captured from somewhere else, possibly the Kuiper Belt, rather than forming in place. Triton's surface was covered in a pinkish layer of frozen nitrogen and methane, with active geysers erupting from the polar regions, driven by solar heating of the translucent ice layer. The surface temperature was minus 235 degrees Celsius, one of the coldest measured surfaces in the solar system at the time. The combination of a captured satellite, active surface geology, and a thin nitrogen atmosphere made Triton one of the most intriguing objects encountered by either Voyager probe. After Neptune, Voyager 2 followed Voyager 1 into the outer heliosphere and eventually across the heliopause. The two spacecraft's exit points from the heliosphere, separated by several decades and billions of kilometers, gave scientists two independent measurements of the boundary. Comparing them revealed something unexpected about the heliopause's structure. When Voyager 1 crossed the heliopause in 2012, measurements showed that the magnetic field outside, in the interstellar medium, was surprisingly well aligned with the magnetic field just inside, on the heliosheath side. This suggested a relatively smooth transition rather than a turbulent mixing region. When Voyager 2 crossed in 2018, some of the same characteristics were present, but there were also differences, including a thin layer of interstellar material detected just outside the boundary. Scientists working with data from both crossings have concluded that the heliopause is not a simple, static boundary, but a dynamic interface that responds to variations in solar wind pressure, changes in the local interstellar medium, and possibly even events like coronal mass ejections from the Sun, propagating all the way out to the boundary. The solar wind's pressure has varied significantly over the course of the Voyager mission. The Sun goes through an 11-year activity cycle, with periods of higher and lower solar wind output, and these variations likely cause the heliopause to expand and contract, breathe in and out, on timescales of years. The interstellar medium that the Voyagers are now sampling is not uniform. The Sun is currently located near the edge of a relatively low-density region called the local cavity or local bubble, a region roughly 300 light-years across that was evacuated by a series of supernova explosions roughly 10 million years ago. The tenuous material inside this bubble has a lower density than the average interstellar medium, and the local interstellar magnetic field has a specific orientation that Voyager's measurements are helping to constrain. Understanding the local interstellar environment matters for reasons beyond pure astrophysics. The flux of cosmic rays reaching the inner solar system, and therefore Earth, is influenced by the properties of the interstellar medium through which the solar system is currently moving. The heliosphere provides some shielding, deflecting lower energy cosmic rays, but higher energy particles pass through. Over geological time, as the Sun has moved through different regions of the galaxy with different densities and magnetic field strengths, the cosmic ray flux at Earth has varied. There is evidence in the geological and paleontological records that suggest correlations between cosmic ray flux variations and climate changes, though the mechanisms and magnitudes are still debated. Voyager's measurements of the present-day local interstellar medium provide a baseline for these long-term studies, a direct measurement of conditions right now that can be compared with proxy records of conditions in the geological past. The question of what the heliosphere looks like from outside is one that scientists have been trying to answer using indirect techniques. The Interstellar Boundary Explorer spacecraft, launched in 2008 and still operating, maps the heliosphere from inside using energetic neutral atoms, particles that carry information about the heliopause boundary but are not deflected by magnetic fields, allowing them to travel in straight lines from the boundary to the detector. These maps suggest that the heliosphere has a roughly spherical shape on the side facing the direction of the Sun's galactic motion, and a more extended, blunt tail shape on the trailing side, somewhat like a comet's wake. But there are significant uncertainties in these maps, and the interpretation depends on models of how the energetic neutral atoms are produced and how they travel. Direct in situ measurements, like those from Voyager, provide ground truth for calibrating these models. The combination of Voyager's direct measurements at two specific points and IBEX's global mapping is a more powerful combination than either alone. Future interstellar probes, if they are built, would provide additional ground truth points and potentially extend the measurements to a much wider range of heliospheric exit directions. Scientists have discussed mission concepts for a dedicated interstellar probe that would be aimed specifically at the nose of the heliosphere, the direction in which the Sun is moving, through the local interstellar medium, and optimized for the science of the heliospheric boundary and the separa-G, interstellar medium beyond it. Such a mission, launched on the fastest feasible trajectory using a solar Oberth maneuver, could potentially reach the heliopause in roughly 15 years instead of the 30-plus years it took the Voyagers. But as of the mid-2020s, no such mission has been approved and funded. The 10 engineers who keep the Voyagers alive today are the inheritors of a long chain of institutional knowledge going back to the original mission designers. Many of the original team members have retired or passed away. The knowledge of how to operate these spacecraft, the specific frequency offset required for Voyager 2's broken receiver, the exact thrust values and timing for the attitude control thrusters given the current propellant load, the thermal limits of specific components based on decades of flight data has been painstakingly preserved through documentation and mentorship. There is a genuine sense in which the operational knowledge accumulated over 48 years of flying these spacecraft is itself an irreplaceable scientific and technical resource. No simulation, no test bed, no classroom can replicate the experience of operating hardware that has been in the interstellar medium for a decade. The team at JPL knows things about spacecraft longevity, about deep space operations, about the failure modes of electronics after decades in the radiation environment of the outer solar system that simply cannot be learned any other way. When the Voyagers finally go silent, that knowledge will remain, and it will inform the design of whatever comes next. The teams who build the next generation of deep space probes will read the documentation from the Voyager mission and find answers to questions they did not know they needed to ask. How does a cryogenically cooled receiver behave after decades of operation? What are the real thermal margins of a radioisotope thermoelectric generator at end of mission? How does an attitude control system degrade after millions of thruster firings? The Voyagers know, and the record has been kept. There is a philosophical dimension to the Voyager mission that tends to come up whenever the spacecraft are discussed. And it is not trivial, even by the standards of hard science. The golden records were not a scientific instrument. They were not intended to collect data or test hypotheses. They were a gesture, an attempt to say something true about humanity to an audience that may not exist. Carl Sagan, who chaired the committee that assembled the record's contents, described the project as a message in a bottle cast into the cosmic ocean. The committee faced an extraordinary curatorial challenge. They had a single disk, a fixed amount of space, and the task of representing all of human civilization to an intelligence that might have no frame of reference for anything terrestrial. They chose 115 images encoded as analog video signals, covering topics ranging from mathematical and physical constants, to human anatomy, to the landscapes of Earth, to structures like the Sydney Opera House and the Taj Mahal. They chose music from more than 24 cultures: Western classical, Eastern classical, jazz, blues, folk traditions from around the world. They recorded greetings in 55 languages, including an ancient Akkadian dialect that has not been spoken as a living language for more than 2,000 years. They included natural sounds: wind, surf, thunder, animal calls, human laughter. The decision about what to include and what to leave out required making judgments about what was essential, universal, and representative of a civilization that is in reality deeply diverse and often internally contradictory. Those judgments reflect the values and perspectives of a small group of people working in the 1970s, and scholars have written extensively about what the records say about the people who made them, as much as what they say about humanity in general. But the intent was genuine: to create an artifact that would outlast everything else humanity had built, carrying a record of what it was like to be alive on this particular planet. Both records are currently approximately 23 to 24 billion kilometers from the Sun, moving in opposite directions. They have been exposed to cosmic rays, to the faint ultraviolet radiation of the interstellar medium, to cosmic dust too sparse to cause significant erosion on any human timescale. The gold plating will not corrode in vacuum. The aluminum cover will protect the disk face indefinitely. The physical medium will survive for a very long time, far longer than any digital storage medium humans have ever built, far longer than any structure on Earth's surface, far longer than the civilization that created them is likely to persist. In this sense, the Voyager records are the most durable artifacts of human civilization. They are the most likely things we have ever made to outlast us. Whether that is comforting or unsettling may depend on one's perspective. The scientific mission of the Voyagers, meanwhile, continues to produce findings that require revising existing models. One of the more surprising recent findings concerns the density of the interstellar plasma in the region Voyager 1 is traversing. Measurements of the electron density in the local interstellar medium, made by detecting the natural oscillation frequency of the plasma, suggest that the density in the immediate vicinity of the heliosphere is higher than pre-mission estimates had suggested. This is consistent with the idea that the heliosphere has carved out a lower density bubble in its immediate surroundings, and that just beyond the heliopause, the density rises again. The measurements are also helping scientists calibrate models of how cosmic rays propagate through the interstellar medium, a question relevant to understanding the radiation environment anywhere in the galaxy. Voyager 1 has also detected waves and oscillations in the interstellar plasma that provide information about the large-scale structure of the magnetic field in the local arm of the Milky Way. These measurements are the first direct in-situ data from the interstellar medium anywhere. Every point along Voyager 1's trajectory is a new measurement, a new data point in a region that was previously accessible only through remote sensing from within the solar system. The interstellar medium through which Voyager 1 is currently traveling is not uniform on small scales. The plasma density measurements have shown variations pockets of slightly higher and lower density that suggest the interstellar medium has turbulent structure on scales smaller than scientists had previously been able to resolve. Understanding this turbulence matters for models of cosmic ray propagation, for models of how the heliosphere responds to external changes, and for models of how interstellar clouds eventually condense into new stars and planetary systems. The magnetic field measurements are similarly nuanced. The field in the local interstellar medium is not perfectly uniform. It has a preferred direction set by the large-scale structure of the galaxy's magnetic field, but there are local variations superimposed on this background. Tracking these variations as Voyager 1 moves through the interstellar medium provides a one-dimensional profile, a single straight-line sample of the field structure in our galactic neighborhood. It is an extraordinarily limited data set by any normal scientific standard. There is one probe, moving in one direction, at one velocity, sampling one thin line through a three-dimensional medium. And yet it is the only data set of its kind that exists. The interstellar medium has been studied for decades using remote sensing spectroscopic observations of starlight passing through interstellar gas, radio observations of pulsars whose signals carry information about the intervening plasma, X-ray observations of hot gas in supernova remnants. These techniques have built up a remarkably detailed picture of the interstellar medium's properties averaged over large regions, but they cannot provide the kind of local, instantaneous, direct measurements that a spacecraft can. The combination of remote sensing and in situ measurement is much more powerful than either alone, just as understanding a planet's atmosphere from orbit is vastly enriched by sending a probe into it. This is part of why some planetary scientists have argued that the scientific return from a dedicated interstellar probe, optimized from the start for interstellar medium science rather than planetary encounters, would be substantially greater than the Voyagers. Even if it carried instruments no more capable, the Voyagers were designed for the planets. Their interstellar instruments were additions, not the primary payload. A mission designed specifically for interstellar medium science would carry a different suite of instruments, would have higher data rates, and would be aimed toward the nose of the heliosphere, the most interesting region for studying the interaction between the solar wind and the interstellar medium, rather than in the directions the Voyagers happened to take, based on the requirements of the planetary encounters. Such a mission has been studied by NASA and the broader scientific community. A concept called the interstellar probe was examined in detail in a study published in the early 2020s, and it outlined a mission that could reach the heliopause in 15 years using a solar Oberth maneuver, a gravity assist that fires a rocket at closest approach to the Sun, where the spacecraft is moving fastest, to add maximum velocity. The mission concept would carry advanced instruments for measuring the interstellar medium, would use laser communications for high data rates, and would have computing systems capable of autonomous fault management. Whether such a mission is built depends on priorities that go beyond science. Deep space missions are expensive and take decades to return results. The scientific community must compete for funding against planetary missions, space telescopes, Earth observation systems, and human spaceflight programs. The case for an interstellar probe is compelling, but so are the cases for missions to Uranus, for a Europa lander, for a Venus atmospheric probe. These decisions are ultimately made through a process of community priority setting that balances scientific value against cost and technical readiness. In the meantime, Voyager 1 and Voyager 2 fly on as the only representatives of humanity beyond the heliosphere. There is a number that puts the distance in perspective. The nearest star to the Sun, Proxima Centauri, a small red dwarf, is approximately 4.2 light-years away. Light travels at approximately 300,000 kilometers per second, and a light-year is the distance light covers in 1 year. 4.2 light-years is approximately 40 trillion kilometers. Voyager 1 is currently about 24 billion kilometers from the Sun. That means Voyager 1 is less than 0.1% of the way to the nearest star. Despite being the most distant human-made object, despite having been traveling for nearly 50 years, it has barely left the solar system's gravitational influence. At its current speed of 17 kilometers per second, Voyager 1 would take approximately 73,000 years to cover the distance to Proxima Centauri. If it were aimed in that direction, which it is not, The actual trajectory will carry it past a star called AC plus 793888 in approximately 40,000 years, at a closest approach of about 1.6 light years. It will not enter that star system. It will pass by, continue on, and drift through the galaxy indefinitely. The galaxy is old enough and large enough that the Voyagers will circulate around the galactic center many times before anything significant happens to them. The Milky Way's disk rotates on a timescale of about 230 million years at the Sun's galactic radius. In that time, the Voyagers will have been flying for so long that any civilization that remembers launching them will be unrecognizable in comparison to the one that exists today. None of this is meant to diminish the achievement. If anything, the immense scale of the cosmos makes the fact of the connection more remarkable. That humans, creatures who existed in a recognizable modern form for only about 300,000 years, who developed writing roughly 5,000 years ago, who built their first electronic computer less than 100 years ago, have managed to throw an object beyond the heliosphere and maintain a communication link with it across 24 billion kilometers is, by any reasonable measure, extraordinary. The signal that left Voyager 1 this morning will arrive at Earth tomorrow morning. Tomorrow, 10 engineers will decode it, assess the state of the spacecraft, and decide what to send back. The day after tomorrow, their commands will arrive at a machine coasting through the interstellar medium, far from home, carrying the sounds of rain and ocean waves and greetings in 55 languages, still listening, still transmitting, still flying. There are questions the Voyagers cannot answer. They cannot tell us whether there are other civilizations in the galaxy. They cannot detect planets around other stars. They cannot measure the properties of the interstellar medium anywhere other than along their own single thin trajectories. They are too slow to reach another star system in any time frame relevant to human planning. In a universe this vast, two small machines drifting through the interstellar medium are almost literally nothing negligible specks in an ocean of space and time. But they are our specks, built by us, launched by us, listened to by us every day. They carry our mathematics, our music, our greetings. They have returned more information about the outer solar system than any other mission. They crossed the first threshold of interstellar space that any human-made object has ever crossed. They have been operating without replacement parts, without hands-on maintenance, without anything more than radio commands transmitted from Earth, for nearly 50 years. That is not nothing. That is, in fact, one of the most remarkable things humanity has ever done. The science is not finished. The link is not yet broken. There are still data packets arriving. There are still commands being sent. There is still a team of people who come into work every day and look after two machines on the edge of the solar system, solving problems that have never been solved before in a place that no one has ever been. And when it does end, when the power finally runs out, when the last signal fades, when the last packet is received and acknowledged and archived, two small spacecraft will continue traveling at 17 kilometers per second, carrying everything we could think to tell the universe about ourselves into the dark. That is the story of the Voyagers. It is a story about engineering and physics and the astonishing scale of the cosmos. But it is also a story about what it means to build something and let it go, to spend 50 years staying in contact with a machine you launched decades ago, to keep listening for the faintest whisper across 24 billion kilometers of space, and to keep sending messages to a spacecraft that cannot come home. The distance grows every day. The signal grows fainter, but the connection holds. Consider what it takes, in purely logistical terms, to send a software update to a spacecraft located 24 billion kilometers away. First, the update must be written. This is not straightforward. The Voyager computers use a programming language called Fortran, a language developed in the 1950s and largely abandoned by the computing industry decades ago. The engineers on the current team must maintain proficiency in a language that predates the personal computer, working within the constraints of hardware that has been in space for nearly 50 years and cannot be modified physically. They cannot add memory. They cannot increase the clock speed. They must work within the original design parameters, patching and updating the software with the care of a surgeon operating on a patient they cannot see and cannot touch. Once the software update is written and verified through extensive simulation on ground-based computers that attempt to replicate the state of the spacecraft's hardware, it must be formatted for transmission. The data encoding follows protocols developed in the 1970s designed to match the original hardware. Even the commands are structured according to specifications that were written before most of the current team was born. The command is then transmitted from one of the Deep Space Network stations, using a 70-meter dish pointed with arc-second precision at a location in the sky calculated from Voyager's known trajectory. The signal takes 23.5 hours to arrive. The spacecraft receives it, decodes it, executes it, and sends back confirmation. The confirmation takes another 23.5 hours to return. If the update does not work as expected, if the spacecraft responds in a way that was not anticipated, the engineering team must diagnose the problem and prepare a corrective command. That process requires another 2 days minimum, assuming the diagnosis is quick. If the problem is subtle, it may take days or weeks of analysis before a new command is ready to send. In 2022, when Voyager 1 began returning corrupted telemetry, the diagnosis took months. The signal was arriving, the spacecraft was functioning, but the data being transmitted was unreadable. The engineers had to reconstruct what was happening at a distance of more than 22 billion kilometers, using only the corrupted data stream as a clue. They eventually determined that a single chip in the flight data system, a memory chip roughly the size of a fingernail, had begun writing data to the wrong memory location, causing the output to be routed through a section of memory that had been inactive for years. The solution required reprogramming the data handling system to bypass the faulty chip and reorganize how data was stored and transmitted, all without being able to touch the hardware. The patch worked, the telemetry cleared. Data from the edges of the solar system became readable again. It was a remarkable piece of remote diagnostics, accomplished using tools and techniques that had not existed when the spacecraft was designed. The communication technology itself has been updated on the ground several times, even while Voyager's hardware remains frozen in the past. The receiving systems at the Deep Space Network have been rebuilt and upgraded multiple times since 1977. The cryogenic cooling systems have been improved. The signal processing algorithms have been rewritten to exploit modern computing power. The error-correcting codes applied to the received signal have been updated to newer, more efficient schemes. The ground segment has kept pace with the best technology available, compensating for the inevitable degradation of the spacecraft end of the link. One of the most significant improvements on the ground side has been the development of Array, combining linking multiple antennas together to act as a single, larger collector. When a mission requires maximum sensitivity, multiple 70-meter dishes can be electronically combined so that their outputs are added coherently, effectively increasing the total collecting area. This technique, which requires extremely precise timing synchronization between antennas, allows the Deep Space Network to hear signals that would be below the detection threshold of any individual antenna. For a mission like Voyager, where the received signal is already at the absolute limit of detectability, this capability is not a luxury, but a necessity. The Deep Space Network itself is a remarkable engineering accomplishment that often receives less attention than the spacecraft it supports. The three facilities, Goldstone in California, near Madrid in Spain, and near Canberra in Australia, collectively represent one of the most sophisticated global telecommunications infrastructure ever built for purely scientific purposes. The antenna structures are engineering marvels. The 70-meter dishes must be steerable to track spacecraft moving across the sky, yet their reflective surfaces must maintain their parabolic shape to within a few millimeters across their entire 7,000 square meter area, despite the stresses of movement, thermal expansion, and wind loading. The Goldstone complex in California has been operational since the early 1960s, initially built to support the early missions to the Moon and Venus. Over the decades, it has grown into a complex of multiple antennas of different sizes, each suited to different types of missions and different frequency bands. The largest antennas, the 70-meter dishes, designated DSS-14 at Goldstone, and similar dishes at the other complexes, were built or upgraded in the 1970s specifically to support deep space missions like the Voyagers. Managing the Deep Space Network's time is itself a complex logistical challenge. Dozens of active spacecraft require communication passes scheduled windows during which an antenna is pointed at that spacecraft and dedicated to its data. Some missions, like the Mars rovers and orbiters, require multiple contacts per day. Others, like the Voyagers, require less frequent but longer passes. The time is allocated months in advance based on mission priorities and scientific requirements. When a crisis occurs like Voyager 2's antenna misalignment in 2023, the scheduling system must be rapidly adjusted to maximize contact time with the affected spacecraft. often at the expense of other missions' scheduled contact windows. The operators who run the Deep Space Network's antennas work around the clock in shifts, monitoring signal quality, adjusting antenna pointing, managing receiver calibrations, and responding to anomalies. The work is technically demanding and requires a detailed understanding of radio frequency engineering, signal processing, spacecraft operations, and the orbital mechanics of both the spacecraft being tracked and the Earth's rotation that determines which stations have line of sight to which parts of the sky. There is a passing of knowledge embedded in the operation of the network that is similar to what happens with the Voyager spacecraft teams. The engineers who design the current antenna systems are mostly retired. The operators who have worked with those systems for decades carry institutional knowledge that does not fully exist in any documentation. New operators learn from experienced ones. Through a combination of formal training and on-the-job mentorship, the way skilled trades have always been passed on. The specific quirks and characteristics of individual antennas this dish has a tendency to drift slightly at low elevation angles. That receiver has a known noise characteristic that must be accounted for in calibration, are part of the operational lore that makes the difference between adequate performance and the kind of extraordinary sensitivity needed to hear Voyager's whisper. It is worth pausing to consider what the data actually looks like when it arrives. Voyager 1's science instruments, the 3 that are still operating, each generate a data stream. These streams are multiplexed together into a single bit stream by the spacecraft's flight data system, which assigns time slots to each instrument and packages everything into frames. Each frame contains a header identifying it, housekeeping data about the spacecraft's health, and the actual science measurements. The frames are encoded with error-correcting codes and transmitted at 40 bits per second. 40 bits per second means that, in one full day of transmission, Voyager 1 sends approximately 3.4 million bits of data. At that rate, downloading a single standard definition movie would take approximately 6 months. Downloading a modern video game would take several decades. But science data is not movies or games. A magnetic field measurement that takes 1 bit requires no downloading time at all, once that bit has been received. The density of information per bit is entirely different from consumer media. What 40 bits per second actually enables, at the distances Voyager now operates, is a continuous stream of physical measurements. The strength and direction of the interstellar magnetic field, measured many times per second. The flux of energetic particles, cosmic rays, arriving at the spacecraft from various directions, binned by energy. The properties of the local plasma, inferred from the resonant frequencies of plasma oscillations. These measurements, sparse as they seem in terms of raw bit rate, represent scientifically irreplaceable data. Each data point is a measurement made in a place no instrument has ever been before. The housekeeping data is equally valuable to the engineers. Temperatures throughout the spacecraft, voltages on the electrical bus, orientation angles, thruster firing records. All of this information tells the team the state of the spacecraft and allows them to anticipate potential problems before they become crises. When the magnetometer boom temperature approached its lower limit as heaters were shut off to conserve power, the housekeeping data gave the team warning in time to adjust thermal management strategies. When a gyroscope bearing showed subtle changes in its precession characteristics, the housekeeping data captured the trend and allowed the team to evaluate whether the gyroscope was approaching failure. The data management challenge on the ground is significant. 48 years of telemetry from 2 spacecraft, combined with the commands sent to them and the engineering analysis conducted over decades, constitutes an enormous archive. NASA maintains this data in the Space Flight Operations Facility at JPL, and it is accessible to scientists worldwide. Researchers who had not yet been born when Voyager launched can analyze decades-old measurements, applying modern analytical techniques to data that was collected by instruments designed half a century ago. This kind of long-term data archive is genuinely scientifically valuable. The ability to go back and look at how Voyager 1's measurements changed over years and decades, to track the slow evolution of the solar wind properties as the spacecraft moved outward, to identify the gradual transition from the heliosphere into the heliosheath and eventually into the interstellar medium, is something that could not be done in real time. Regardless of how sophisticated the instruments were, understanding slow processes requires long baselines. The Voyager archive provides a baseline nearly 5 decades long for regions of the solar system and interstellar space that have never been measured by anything else. Future researchers will continue to mine this data as new theoretical models are developed and new questions are asked. It is likely that some of the most important insights from the Voyager mission have not yet been extracted, waiting for the right question, the right analysis technique, or the right theoretical framework to make them legible. This is a common pattern in long-duration missions. The initial analysis captures the obvious discoveries, but decades of subsequent work reveal subtler patterns and relationships that were not visible in the original data reduction. The legacy of the Voyager mission also extends to the culture of space exploration in ways that are harder to quantify, but no less real. The Grand Tour concept, the first detailed reconnaissance of the outer planets, the discovery of active volcanism on Io, the characterization of Titan's atmosphere, the exploration of Uranus and Neptune, the crossing of the heliopause. These achievements inspired generations of scientists and engineers who went on to design and operate subsequent missions. The scientists who built the Cassini mission to Saturn, the Galileo mission to Jupiter, the New Horizons mission to Pluto, and the Juno mission to Jupiter were in many cases directly inspired by Voyager results. The engineers who designed more reliable and capable deep space spacecraft built on lessons learned from operating the Voyagers through crisis after crisis. The planetary science community that emerged from the Voyager era is broader and more capable than it would have been without those missions. The techniques developed for navigating spacecraft using planetary gravity assists for operating deep space missions with limited communication bandwidth, for diagnosing hardware failures from billions of kilometers away. All of these techniques became the foundation of subsequent mission operations. Every deep space mission flown since the Voyagers has benefited from the operational experience and engineering knowledge accumulated during those missions. There is also the matter of what the Voyager mission revealed about the solar system as a place of extraordinary diversity. Before Voyager, the outer solar system was largely unmapped. The giant planets were dots of light in telescopes, their details accessible only through indirect inference. Their moons were points of light with known orbits. The rings of Saturn were known but poorly resolved. The possibility of active geology on outer solar system moons was not seriously entertained by most planetary scientists. After Voyager, the outer solar system was a place of astonishing complexity. Active volcanoes on Io, an ocean of ammonia-laced slush, possibly lurking beneath the ice crust of Europa, a thick nitrogen atmosphere on Titan, geysers of nitrogen ice on Triton, rings of extraordinary intricacy around all four giant planets, dozens of newly discovered moons, ranging from smooth spheres to chaotically shaped rubble piles. This was a solar system that had revealed itself to be far stranger, far more varied, and far more dynamic than anyone had predicted. That revelation drove the subsequent generation of outer solar system exploration. The possibility of a subsurface ocean on Europa, first suggested by Voyager data and later confirmed by Galileo, has made Europa one of the highest priority targets in the search for life beyond Earth. The discovery of Titan's atmosphere inspired the Cassini-Huygens mission's descent of the Huygens probe into Titan's atmosphere. In 2005, the most distant successful planetary landing ever, attempted. The mystery of Neptune's active weather and Triton's active geysers motivated proposals for future missions to the ice giants that continue to be discussed today. All of this scientific and programmatic consequence flows from two spacecraft that were designed in the 1960s and launched in 1977, on a trajectory made possible by a planetary alignment that comes around only once every 176 years. The timing was, in retrospect, almost miraculous. If Gary Flandreau had not been working at JPL in 1964, had not been assigned the specific trajectory calculations that led him to notice the planetary alignment, he had not recognized its implications. The window would have closed in 1978 and would not reopen until the 21st century. The entire outer solar system reconnaissance that shaped modern planetary science might have been delayed by decades. But Flandreau was there. He noticed. The engineers built the spacecraft in time. The probes launched successfully. And now, nearly 50 years later, they are still out there, still transmitting, still teaching us things we could not have learned any other way. The sun is approximately 4.6 billion years old. The solar system has been in existence for essentially the same length of time. Against that backdrop, 50 years is nothing less than a single grain of sand on a very large beach. And yet in those 50 years, two small machines have crossed the heliopause, entered interstellar space, and sent back data from a region of the universe that was inaccessible to science for the entire preceding history of the cosmos. Every time a new discovery is announced from the Voyager mission, a new measurement of the interstellar magnetic field, a new characterization of the local plasma density, a confirmation of a theoretical prediction about the heliopause structure. It is the result of hardware that was designed before the internet existed, before personal computers existed, before mobile phones existed, running software written in a programming language that is considered obsolete, transmitting data at 40 bits per second across 24 billion kilometers to antennas that cool their receivers to 4 degrees above absolute zero in order to hear a signal weaker than anything in everyday experience. It works because the people who built it were extraordinarily good at their jobs. It works because the people who have maintained it for 5 decades have been equally extraordinary. It works because the physics of radio wave propagation and antenna design and cryogenic cooling are understood with precision. It works because the solar system is large but not infinite, and because signals traveling at the speed of light, while slow on cosmic scales, are fast enough to maintain a conversation across planetary distances. And it will keep working for a few more years. The power curve will continue its slow decline. The instruments will be shut down one by one. The team of 10 will keep coming to work each morning and listening for the signal. The data will keep arriving, 40 bits per second, from the edge of our solar neighborhood. The day will come when the last data packet is received and the signal disappears into noise. On that day, humanity will have lost contact with the most distant object it has ever built. 2 spacecraft will continue their silent journey through the galaxy, carrying the sounds of a living world on gold discs in the dark. But before that day comes, there is still science to do. There are still measurements to take, still questions to answer, still data to collect from a region of space that no instrument has ever sampled before. The Voyagers are still working. The link is still open. The conversation continues. It is worth appreciating what we mean when we say the Voyagers have entered interstellar space, because that boundary is not a line drawn on a map. It is a physical phenomenon with a specific cause, and understanding it reveals something fundamental about how stars interact with the galaxy around them. The sun, like every other star, is constantly shedding material. Not slowly, not in isolated bursts continuously, in every direction at once. This outflow, called the solar wind, is a stream of charged particles, mostly protons and electrons, moving at speeds between 300 and 800 kilometers per second. This plasma fills the entire volume of the solar system, exerting pressure outward in all directions. The boundary of the heliosphere is simply the place where this outward pressure is finally balanced by the pressure of the material filling the space between stars. That interstellar material, the interstellar medium, is incredibly thin by any everyday standard. We are talking about roughly 1 atom per cubic centimeter in some places, compared to approximately 10 million billion atoms per cubic centimeter in the air we breathe. Yet the solar wind, by the time it reaches tens of billions of kilometers from the sun, has thinned so dramatically that this nearly empty interstellar gas and its associated magnetic field are enough to push back. The result is a bubble. The heliosphere is a vast, roughly spherical or perhaps more comet-shaped region carved out by the solar wind in the surrounding interstellar medium. Everything inside this bubble is in some sense part of the sun's domain, bathed in its plasma and magnetically connected to it. Everything outside is genuinely interstellar space, governed by the physics of the galactic medium rather than by our star. Before Voyager, we could only infer where this boundary was and what conditions might be like there. Theoretical models had predicted the general existence of the heliopause for decades, but the actual location, the specific character of the transition, the properties of the plasma on both sides, these were unknown. The heliosphere could have had a sharp boundary or a gradual one. The interstellar magnetic field could have been organized or chaotic. The plasma conditions just outside could have been very different from what the models assumed. When Voyager 1 crossed into interstellar space in 2012, it provided the first direct answers to those questions. The boundary was relatively sharp, not an abrupt wall, but a transition region considerably narrower than the theoretical maximum. The plasma density increased as expected. The magnetic field changed direction. The galactic cosmic ray flux high-energy particles from outside the solar system increased dramatically, confirming that the heliosphere had been shielding the spacecraft from a significant fraction of this radiation. That last point is scientifically and practically important. Cosmic rays are energetic particles, mostly protons, accelerated to near light speeds by violent events elsewhere in the galaxy, particularly supernova explosions. They travel through the galaxy in curved paths, guided and scattered by the galactic magnetic field. And when they reach the heliosphere, the solar wind's magnetic field deflects the lower energy ones. The heliosphere filters out a significant fraction of the cosmic ray population before it reaches the inner solar system. When Voyager 1 crossed the heliopause, the instruments registered a sharp increase in the number of cosmic rays hitting the spacecraft. The galactic cosmic ray flux outside the heliosphere turned out to be roughly twice as high as inside. This means that the heliosphere reduces the cosmic ray dose received by any unshielded surface in the inner solar system by approximately a factor of 2, compared to what it would receive in open interstellar space. For future crewed missions beyond the heliosphere, a concept that remains deeply speculative given the distances involved, this measurement has direct implications for radiation shielding requirements. For understanding Earth's long-term geological and biological history, it raises questions about how the cosmic ray flux at Earth has varied over time, as the sun's activity has changed, and as the solar system has moved through different regions of the galactic disk. The sun, after all, is not stationary. It is orbiting the center of the Milky Way at roughly 220 kilometers per second, completing one orbit approximately every 225 million years. As it moves, it passes through regions of the galactic disk with different densities of interstellar material, different magnetic field strengths and orientations, different proximity to star-forming regions, and the remnants of past supernova explosions. The heliosphere's size and shape vary in response to the external pressure of the surrounding medium. When the solar system passes through a denser region, the heliosphere contracts. When it passes through a more diffuse region, it expands. We are currently in an unusually low-density region. The local bubble, the cavity within which the solar system currently resides, has a density perhaps 1/10 of the average interstellar medium density. This means the heliosphere is currently larger than average. In the geological past, when the solar system was passing through denser regions, the heliosphere would have been smaller, less protective, and more cosmic radiation would have reached Earth's surface. Some researchers have proposed connections between these cosmic ray variations and events in Earth's geological and biological history. Periods of elevated cosmic ray flux might correlate with periods of higher mutation rates, with ice ages, or with extinction events. The evidence for these connections remains debated, and the mechanisms are not fully established, but the underlying physics is real. Cosmic rays do interact with Earth's atmosphere, producing secondary particles and affecting atmospheric chemistry. Galactic dynamics do control the sun's path through the interstellar medium. The heliosphere's size does vary with the surrounding medium's properties. Voyager's measurements of the current interstellar medium, the density, temperature, magnetic field, and cosmic ray environment just outside the heliosphere, provide the baseline against which any models of past variation must be calibrated. You cannot know how unusual the present is without measuring it. Before 2012, nobody had ever measured the interstellar medium directly from inside it. Now we have those measurements, and they matter for questions that extend far beyond spacecraft engineering. The plasma wave instrument on Voyager 1, one of the 3 remaining active instruments, has been particularly valuable for characterizing the interstellar plasma environment. This instrument does not directly detect plasma particles. Instead, it measures oscillations in the electric field that arise when the plasma is disturbed by the spacecraft itself, by solar events that propagate outward and eventually reach Voyager's position, or by the natural wave modes of the interstellar medium. From these oscillations, scientists can infer the local electron density. Remarkably, the plasma wave instrument has detected several episodes of enhanced plasma oscillations that turned out to correspond to large coronal mass ejections from the sun, explosive eruptions of solar plasma that propagate outward through the heliosphere, and eventually, many months later, arrive at Voyager 1's position in interstellar space as a pressure pulse. When this pulse arrives, it disturbs the surrounding plasma, generating oscillations that the instrument detects. By measuring the frequency of these oscillations, scientists can calculate the electron density of the interstellar plasma at Voyager's location. This is remarkable for 2 reasons. First, it demonstrates that solar events can propagate all the way into interstellar space and still have measurable effects. The heliosphere is not a perfect barrier, but a permeable one. Second, it has allowed scientists to make precise measurements of the interstellar electron density at multiple points along Voyager's trajectory over the years since the heliosphere crossing, tracking how that density varies with distance from the heliopause. The measurements show that the interstellar electron density is increasing as Voyager moves farther from the heliopause. The heliosphere carves out a low-density cavity, and as Voyager moves away from the boundary, it is moving into denser interstellar material. This gradient in density is exactly what theoretical models of the heliosphere-interstellar medium interaction predicted. But this is the first time it has been directly confirmed by measurement. Each of these data points, each oscillation frequency measured by the plasma wave instrument, each magnetic field reading from the magnetometer, each cosmic ray count from the particle detector, is a piece of knowledge about a region of the universe that was previously inaccessible. Future interstellar probe missions, if they are designed and built, will be able to compare their measurements with Voyager's and track how the local interstellar medium has changed over the decades between mission operations. This kind of temporal baseline, extending over human timescale changes in the interstellar environment, will be scientifically valuable in ways we cannot fully predict. What we know for certain is that the universe beyond the heliosphere is not a uniform void. It has structure, density variations, magnetic field geometry, plasma wave activity, cosmic ray fluxes that vary with direction and energy. Every measurement Voyager makes is a pixel in a picture of that structure, and we are just beginning to understand what the picture shows. The team of 10 people at JPL knows this. They come in every day to a job that most of the world has forgotten exists, maintaining a connection to objects that most people have never thought about. They troubleshoot hardware they cannot inspect, diagnose problems in systems designed before they were born, and send commands to machines so far away that the reply will not come until the day after tomorrow. They have done this through equipment failures, through power crises, through software corruption, through antenna misalignments, through the quiet daily discipline of keeping the link alive. They will keep doing it for a few more years. And when it finally ends, when the last data packet is received and the signal fades into the background noise of the cosmos, the record they have kept, 48 years of telemetry, of commands, of engineering decisions, and scientific discoveries, will remain. Future scientists will return to that data for decades, finding in it answers to questions that have not yet been asked, fitting Voyager's measurements into theoretical frameworks that have not yet been developed, using the data to calibrate models of a universe that we are still only beginning to understand. There is one more dimension to the Voyager story that tends to get lost in discussions of engineering and physics: the human dimension of what it means to say goodbye slowly. The scientists who built the original instruments on the Voyagers, who designed the magnetometers, the plasma wave detectors, the ultraviolet spectrometers, the camera systems, did so knowing that the instruments would outlive their involvement with them. The principal investigators who proposed the science instruments, wrote the grant proposals, assembled the teams, and spent years in calibration laboratories, making sure their detectors would work correctly in deep space. Most of them are now in their 80s or older, or have passed away. Ed Stone, the project scientist for the Voyager mission who held that role for more than 4 decades, stepped back from active leadership in his 80s after a career defined largely by these 2 spacecraft. These were people who spent their professional lives attending to 2 machines in the void. They watched the data come in from Jupiter, from Saturn, from Uranus, from Neptune. They watched the spacecraft cross the termination, shock the region where the solar wind slows from supersonic to subsonic speeds, and then the heliopause. They argued about interpretations, published papers, revised models, taught students who went on to design subsequent missions. Their entire scientific careers were intertwined with the trajectory of 2 spacecraft launched in a year when the first personal computer had not yet appeared on the market. The instruments that are still running the magnetometer, the plasma wave instrument, the cosmic ray subsystem, are the instruments whose principal investigators, or their intellectual successors, are still able to analyze the data as it comes in. The instruments that have been shut down represent science that will not be continued, questions about the interstellar medium that will have to wait for the next probe. There is a particular poignancy to shutting down a scientific instrument on a spacecraft that is never coming home. When the ultraviolet spectrometer on Voyager 1 was turned off to save power, the science it had been collecting measurements of the ultraviolet background radiation from distant galaxies. Observations of hydrogen in the outer heliosphere came to an end. The instrument itself did not die. It is still physically attached to the spacecraft, still attached to the wiring harness, still potentially capable of functioning if power were available, but the power will never be restored. The science ended, not with a hardware failure, but with an accountant's calculation about how to allocate 210 watts across competing needs. Every instrument shutdown is a decision about what matters most in the remaining time. The team must weigh the scientific value of each measurement against the power cost of obtaining it, knowing that every watt spent on one instrument is a watt not available to keep the computers and transmitter running. They must do this with instruments that have been in space for nearly 50 years, instruments whose behavior and sensitivity have drifted from their original calibration in ways that must be tracked and corrected through careful analysis. It is a remarkable kind of stewardship. The team is caretakers of something they did not create and cannot replace. They inherited a mission already in progress, with hardware they have never seen in person, running software written before most of them entered the field. They are responsible for keeping alive the most distant human-made objects in existence, for as long as physics allows. And they do it well. The Voyagers have outlasted every design requirement, every original projection, every reasonable expectation. They were designed for 5 years. They are approaching 50. That ratio, 10 times the design life, is not unprecedented in the history of NASA missions, but it is rare, and it is a testament both to the original engineering margins and to the quality of the ongoing operations. When the power finally runs out and the transmissions stop, the Voyager mission will have returned a quantity and quality of scientific data that no single mission in the history of planetary science has matched in terms of sheer scope. First, close-up imagery of all 4 outer planets. Discovery of active volcanism in the outer solar system. First and only visits to Uranus and Neptune. Discovery of multiple previously unknown moons and ring systems. Confirmation of Titan's atmosphere and its implications for the chemistry of life. And finally, the first direct measurements of the interstellar medium and the first crossing of the heliopause by a human-made object. That is the legacy. Not the golden records, though those are extraordinary in their own right. Not the photograph of the pale blue dot, though that image has become a cultural touchstone for the fragility and isolation of our world. The scientific legacy is the data, tens of billions of bits of it, collected over nearly 50 years, from a mission that was designed for 5. The signal is faint. It takes a day to arrive. It carries 40 bits per second of irreplaceable measurements from beyond the solar system. And somewhere in the Mojave Desert, or outside Madrid, or near Canberra, a 70-meter dish is pointed at a precise location in the sky, its receiver cooled to 4 degrees above absolute zero, listening for a whisper that crossed 24 billion kilometers to reach it. The story of how that signal was found, and how it has been maintained, is also a story about the slow accumulation of engineering knowledge across generations. When the original Voyager team designed the communication system in the late 1960s, they were working at the edges of what was technically possible. The sensitivity they needed to receive Voyager's signal from the outer planets required receiver technology that had only recently become available. The signal processing techniques they used were state-of-the-art for their time, but they knew that the spacecraft would outlast the technology it launched with. They built the spacecraft hardware to last, but they assumed the ground systems would be upgraded to keep pace with advancing capability. That assumption turned out to be exactly right. Every major improvement in the link between Earth and the Voyagers since launch has come from the ground side. Better receivers, better cooling systems, better signal processing algorithms, better computers to run those algorithms. The ground segment has been continuously modernized, while the spacecraft hardware has remained unchanged. This asymmetry in the ability to upgrade is one of the fundamental realities of deep space operations. You can maintain and improve everything on Earth, but once a spacecraft is launched, the hardware it carries is fixed. This creates a design philosophy that has persisted in deep space engineering to the present day. Build a spacecraft with margins more power than you need, more redundancy than seems necessary, more structural strength than the launch loads require. Because once it is gone, you cannot add anything. The spacecraft will degrade, and everything you can do about it will have to be done through software, through command sequences, through the intelligence and creativity of engineers on the ground, who will work with whatever hardware survives. The Voyager team built those margins in. The radioisotope thermoelectric generators were sized to provide far more power than the spacecraft needed in its first years. The propellant reserves were generous. The computer memory, though tiny by modern standards, was sufficient for decades of additional software updates. The structural margins, the factors of safety, built into the mechanical design, were conservative enough that a spacecraft designed for 5 years has survived 50 without any structural failures. And the people on the ground have been creative and resourceful enough to use those margins well. Every crisis the Voyagers have faced has been met with a solution. The broken backup receiver in 1978 became a known characteristic that engineers have worked around ever since. The corrupted memory chip in 2022 was bypassed through software. The misaligned antenna in 2023 was corrected by shouting a single command at 250% power across 20 billion kilometers. Each of these solutions required not just technical skill, but the particular kind of ingenuity that comes from understanding a system so well that you can reason about its behavior in failure modes that were never anticipated in the FAFT. Original design. The engineers who solved the backup receiver problem in 1978 could not have consulted a manual that described the broken capacitor's behavior, because that behavior was not known before the failure occurred. They had to infer it from indirect evidence, reason about the physics of what a capacitor failure would do to a receiver circuit, test their hypothesis against the available data, and design a workaround based on their model of the problem. That kind of reasoning, the ability to understand a complex system deeply enough to diagnose it from incomplete information at extreme remove, is the core competency of the Voyager operations team. It has been built up over decades, passed from one generation of engineers to the next, documented in operations logs and technical memoranda and informal institutional knowledge that no document could fully capture. The knowledge that the current team carries is irreplaceable in the strict sense. If the team were disbanded and the knowledge not transferred, restarting operations would be extraordinarily difficult. The telemetry format, the command encoding, the specific frequency offset for Voyager 2's broken receiver, the thermal model that predicts how components will behave as the heaters are turned off one by one. All of this exists in a combination of formal documentation and experienced judgment that cannot be reconstructed from first principles without significant effort. This is one reason why the operations team has been careful to document their procedures and to train successors who understand not just what to do, but why. The eventual end of the mission is known in advance, and there is time to prepare for it. The scientific archive will outlast the operational team. The data will be available for future researchers. The engineering knowledge will be captured in technical reports that can inform the design of future deep space missions. But the lived experience of operating a spacecraft for 50 years through repeated crises and recoveries that is harder to transfer. Some of it will be lost when the last member of the original team is gone, just as some of the knowledge from the original designers was lost when they retired. Future deep space engineers will be better for the documentation and training they receive from the Voyager team, but they will be working at some degree of remove from the original experience. This is the natural cycle of engineering knowledge in long-duration programs. Expertise is built, documented, transferred imperfectly, and rebuilt in a new generation that brings its own understanding and perspective. The mission changes, the spacecraft degrades, the challenges evolve, and each generation of engineers responds to the specific problems they face with the tools and knowledge available to them. The continuity is maintained, but it is never perfect, and the knowledge that is lost is sometimes only recognized later when a problem arises that the absent expertise would have recognized immediately. It is a human story, as much as a technical one. The Voyager mission has been running for longer than most careers last. The people who started it have retired or died. The people who are finishing it were children when it began. Between them, they have maintained a conversation with two spacecraft that has not been interrupted for 48 years, across a communication link that operates at the absolute limits of physical possibility. That conversation will end, but the spacecraft will not stop. The data will not be erased, and the knowledge, imperfect and incomplete, as all human knowledge is, will persist. The cosmos does not notice a single faint signal from a small world on one arm of one galaxy, but the people who sent that signal, and who have listened for its reply every day for nearly 50 years, have built something that will outlast them. That is what the Voyager mission is. Not just an engineering achievement, not just a scientific program, an act of sustained attention across nearly 50 years to two machines flying further from home every day. A refusal to let go of the connection for as long as physics makes it possible to hold it. Final character count. What makes the Voyager mission distinctive in the history of science is not just what it discovered, but how those discoveries kept happening, decade after decade, long after the mission's primary objectives were completed. Most space missions have a defined active phase: a launch, a cruise, a primary science phase, and then either a controlled end or a steady decline into silence. The Cassini spacecraft, for example, completed its primary mission at Saturn, and was then deliberately directed into the planet's atmosphere to prevent contamination of potentially habitable moons. The New Horizons mission flew past Pluto in 2015 and then received a mission extension to visit a Kuiper Belt object. These extensions are valuable, but they are bounded by fuel, by power, by the practical limits of hardware operating far from its nominal design conditions. The Voyagers are different. Their mission has never really ended. It has evolved. What began as a planetary reconnaissance mission became an outer heliosphere mission, then an interstellar medium mission, each phase enabled by the spacecraft's continued function and by the scientific community's recognition that the measurements available at each new position were scientifically unique. This evolution was not fully planned. The original Voyager mission design documents describe a 5-year primary mission to Jupiter and Saturn, with Voyager 2's extended mission to Uranus and Neptune as a contingency. Nobody wrote a plan for interstellar medium science in the 1970s, because the spacecraft was not expected to survive that long. The interstellar phase of the mission exists because the hardware exceeded its design life by a factor of 10, because the team found ways to manage the declining power budget, and because the scientific community recognized the unique value of the measurements being made. This is an important lesson for the design of future long-duration missions. The science you will do at the edge of the solar system cannot be fully anticipated when you are designing a spacecraft to fly to Jupiter. But if you build with appropriate margins, if you design the systems for graceful degradation rather than abrupt failure, and if you support the operational team that will fly the spacecraft for decades beyond the primary mission, the unexpected science will happen. The spacecraft will outlast the original plan, and the discoveries it makes will be the ones that define its legacy. The heliosphere, crossing in 2012, the moment Voyager 1 became the first human-made object to reach interstellar space, was not in the original mission plan. It happened because the spacecraft still worked, because the team was still there, because the Deep Space Network had been maintained and upgraded, because the scientific community had advocated for continued operations funding year after year, making the case to program managers and budget committees that the measurements being returned justified the cost. That advocacy matters. The Voyager mission has required sustained investment of public funds for nearly 5 decades. The cost of operations has been relatively modest compared to the cost of new missions a few $1,000,000 per year in recent years, for a team of 10 people and a share of Deep Space Network time. But it has required continued justification in an era of competing scientific priorities. The mission has survived because the scientific community has consistently argued that the unique measurements being returned cannot be obtained any other way, and they have been right. This is the context in which the eventual end of the Voyager mission should be understood. When the last signal is received, it will not mean that the mission failed or that it is time to move on. It will mean that a mission that far exceeded every reasonable expectation has finally reached the end that physics requires. 2 spacecraft, designed for 5 years, will have lasted 50. They will have discovered active volcanoes in the outer solar system, explored 2 planets never visited before or since, crossed the heliopause, and measured the interstellar medium directly for the first time in history. And then they will continue their silent journey, carrying a gold record, moving at 17 kilometers per second, into the dark between the stars.